We've been hearing a lot about the arrow of time, and I'd like to talk a little bit about what does it mean for the arrow of time to turn around. Arrows don't like to do this, but sometimes they can. So we heard this quote before. This is just the last part of Eddington's. The law that entropy increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. You have to collapse in deepest humiliation. But if the second law means the law that entropy always increases, then it's just not true. Entropy does occasionally decrease. So we heard Max talk about entropy decrease just from learning more information about a system. But it'll also decrease if you just wait. So this is Poincaré recurring. So there are Poincaré recurrences. As we know, a system will eventually return to its initial state. And I apologize to a couple of you who were at a meeting before, and a couple of jokes will be old. But also, just in small enough systems, you can see thermal fluctuations will cause entropy decreases. It's actually been seen, so there have been some papers looking at small systems and measuring experimentally small decreases in entropy. Now, these don't quite violate the second law of thermodynamics if you just have a more subtle version of the second law, which is that there are entropy increases and decreases, and if over a certain amount of time, the probability of the entropy going up by some amount is exponential in the entropy difference, exponentially more likely than entropy going down. So that's just a more refined version of the second law, which is more useful. So what I'd like to talk about is first the fact that entropy does decrease. I've sort of done that occasionally, even in closed systems. Then the key point that an entropy decreasing fluctuation really is like a reversal in the arrow of time in a specific way that I will explain. Then this can help us to explain various nucleation and transition processes and eternal inflation and shed light on the structure of eternal inflating spaces. Of course, you can think of it in all kinds of other contexts that are long enough lived to have entropy decrements, but eternal inflation is one where you have eternity, so it gets particularly interesting. Then I'll talk about a sort of corollary, which is that if you have a minimum in entropy, you can think of that minimum, some region or some time and minimum entropy state, you can sort of think of that as a time reversal surface where the entropy arrow of time flows away from it in both directions, and that's really the arrow of time. And talk about time symmetric cosmologies that become important. So 2 years ago, I gave an early version of the same talk, and some of you may remember this piano, and you know what's going to happen to it. So if you put this piano in a closed box and just let it sit forever, what will happen to it is eventually the piano will, the air atoms will knock off little bits of the piano, some strings will snap every once in a while and lead to some loud sounds. Eventually the piano will collapse if there's gravity also in this box, but I'm not going to think about gravity in terms of self-gravity. It'll further decay, and eventually you'll end up with kind of a gas of piano materials that'll be a nuclear statistical equilibrium. Then if there's baryon decay, it'll eventually just be some leptons and photons at very high entropy. So the entropy of the piano goes from a ordered 10 to the 26 to 10 to the 39. Now, if we just watch that equilibrium box, we can decrease the entropy by hand if we reach in and gather all this stuff in one corner. We can do that, of course, but that will cost me entropy to do that. But I want to talk about closed systems here. But another thing we can do, of course, is just wait for a really long time. Again, exponential in how much entropy how much we want the entropy to go down. And if we wait long enough, we'll get a little, maybe gathering of gas together in some little region of the box. And almost certainly it will then just return back to equilibrium. Now, if we get really patient, we can wait for, say, a frog to appear in the box, right? And after a while, and the frog will die and decay back to equilibrium. We can wait for a while longer, and a more massive thing like a bowl of petunias will nucleate, and we can look at it for a little while. If we wait a really long time, we can get a bigger, that is the same sort of mass of a piano of stuff nucleating as an object, but it won't necessarily look like a piano. We can wait longer and longer until it might look like a, say, broken piano, or even a not that broken piano. Or and if we wait a really, really long time, we might eventually get, after many heartbreaking failures, a full piano. Now, the contention that I want to make is that if we just say, I'm going to wait for there to be a piano in this box, no matter how long it takes, and I ask the question, if I wait and if I get a piano, I can ask the question, how did I get there? What was the sort of sequence of states that I went through to get to the piano? That in fact it's just like this. The box sort of slowly congeals into some atoms, and those atoms gather together and build the piano laboriously. It makes a collapsed piano, which will suddenly right itself at some point. Some air will gather together and create sound waves that condense on strings and fuse them together so that they're strings in a piano. And finally, it will polish itself up. And that's how you will get a piano. Now, this sounds a little bit absurd. This is exactly the time reverse of how the piano decayed into equilibrium. But the contention is that this is exactly how it would be, most probably. Of course, there are many detailed ways in which the piano could decay. One leg might break first, one string might break first. And so there will be many ways of recreating the piano, but statistically speaking, they will be the same as the time reverse of the ways that it broke. So for this, I'm going to give a sort of classical argument that will give the basic idea and then refer you to a paper for a quantum version as well, and a more detailed version of the classical one. So the classical setup is going to be much like some talks we've heard before, laying out, let's suppose we have this closed system that has a fixed set of microstates. We'll call them A sub I. And we can suppose we can assign a probability P sub I to each one of them. And then we want to assign to each microstate a macrostate. We'll call those macrostates big A sub j. And we can give each macrostate a probability by just summing up over the probabilities of the microstates that are in it. Now I'm going to assume, we've assumed, and I should mention that this part is work with Sean Carroll and Matt Johnson. So we assume that these microstates evolve according to some unitary operator, and in particular, the assumption that we're going to make is that the evolution operator of these microstates is such that it is time reversible in a sense, and in more particularly, that for each trajectory A of t, there's a kind of barred trajectory, A bar of minus t, that is also a solution to the same evolution equations. So this bar is something that, when applied twice, gives you back the original trajectory. And this, so for classical mechanics, this would be like reversing the momentum and reversing the time evolution. For quantum mechanics or quantum field theory, this would be CPT. So it's a symmetry that involves time reversal. Okay, so then, given these probabilities for the microstates at some initial time, then this evolution operator also induces some evolution of the micro-probabilities, which I believe is what David Albert called the metaculus, which I love that word. I will now introduce the macrometaculus, which is something you can also calculate, which is the evolution of the macrostates, which is just induced by the evolution of the metaculus. Okay, so what this looks like on a diagram, so this is a diagram that's cooked up to have all the features of phase space that are necessary here. So this is phase space, so there are lots of little microstates. I've partitioned it into these macrostates labeled by the big A's. And this dotted line is meant to show represent this mapping, this involution. So if I apply the bar operator, I would go from, say, a point above that dotted line to a point reflected across that dotted line. Now, so I can suppose my system just starts out at some early time and it's in this state, this macro state A naught. It might be on some micro trajectory like that blue line that goes up there. Now, it might have come from some lower entropy macro state. That's what we expect about the physical world we see, that the past hypothesis is that earlier on it was in some lower entropy macro state, but it might not, so in this case it is. Here's one that passes through A naught, but coming from a higher entropy macro state, and that's what we would more generically expect if we just took some random microstate that's in A naught. So that's this trajectory here, and this other one is the barred trajectory that I was mentioning. It's just a reflection across the axis. Okay. So what does it mean to say that the arrow of time reverses? So the idea is we consider all this and we compute this macrometaculus, I guess, of the big P sub j's, how the macro states evolve in time, the probability distribution over macro states, how that evolves in time. That's a full description of the macroscopic evolution of the system. And now I can consider barring that in the sense that I take each microstate, I compute its bar, its time-reversed evolution, and I assign each A's probability to its bar. So this is sort of time reversing this whole macroscopic probability distribution. It's saying if I just reversed all these microstates, what is the probability distribution over macrostates that I would get? The claim is that if we just sit around, we start in equilibrium, we sit around and wait for some macro state A naught to come into being, okay? That was the question. Then the way that it got there is given by the bar time reverse of how it goes from A naught bar to equilibrium. Okay, so that takes a little bit of explaining exactly what that means. So suppose I want to know, here's the case where I just want to sit around and wait until the system passes through A naught. It started up there in equilibrium, and sometime later it passes through A naught. And so what I say is, okay, let me take this system that starts in A naught bar, that's this macro state, let me see how it evolves. So it's made up of microstates that go like this. This is one of them. And I can just compute using my normal reasoning for how something like that would evolve. That's like the piano decaying. Then I have to bar time reverse that, and that gives me how I got to the macro state that I wanted to wait for. And the basic argument for this is essentially what I just gave. So if I want to know how a normal thermodynamic system evolves, a reasonable way to think about it is to say that I specify the macro state, and then I assume that all microstates associated with that macro state are equally probable, because all I know is the macro state. So the most reasonable thing I can assume is that they're equally probable. That's how we get normal thermodynamic evolution, and where it's highly probable that as I evolve away from that macro state, I'll evolve into other higher entropy macro states. Here I'm saying I want the set of all microstates that go into A naught such that they're all equally probable. Well, that's easy to calculate because of this symmetry. I start here, figure out all the microstates that go out of here with equal probability, and basically by barring, I get the exact set of states that I wanted. But exactly the evolution of these states, where I start all in A bar with equal probability, is just the natural thermodynamic evolution of A naught bar. So, and I'll give a few examples of how you would do this in practice. So with the piano, the contention is, if I want to know how I formed a piano, well, I'd first actually technically have to start with an anti-piano, and if my original piano was like sliding to the right, I'd start with a piano sliding to the left. So I'd start with my, say, left sliding anti-piano made out of anti-baryons and stuff, ask how it decays to equilibrium. That's going to be pretty much the same thing as what I described before. Then to get the creation of a piano, I'd bar all that. That turns the anti-piano into a piano, and it turns my left-moving piano into a right-moving piano, and the evolution goes from equilibrium through all those states just as I described, the exact sort of time reverse back to the piano that I was waiting for. You can really get some insight into systems that, I find there are different reactions to this argument. A lot of people say, well, yeah, I kind of knew it had to be that way. And I think that's fair enough. We haven't managed to find it written down anywhere, but maybe it is, because it is, in retrospect, gets sort of obvious. The other is that can't possibly be true, because how would it be the most likely to go through all these unlikely things? Why don't you just kind of fluctuate the thing all at once? That seems much more easy to do than going through all these intermediate steps. And I think many people, I carried around that intuition until realizing that this had to be true. So one example where I think people have this idea that these things pop into existence really quickly is these Boltzmann brains that Raphael was talking about. The idea is that these are the smallest fluctuation from equilibrium that can account for my observations, whatever those are. It's just a brain in a little life support system, this nutritive broth that I've given it here. Now, so if I ask, how did one of these nucleate? I first have to turn it into an anti-brain, but that's not important. Let me just let it go. So it's just out in empty space, so it quickly cools off and freezes. Maybe the glass jar breaks and shatters, and then I just have this frozen brain that's sitting around. And that sits around for an exceedingly long time. You can find anything on Google Images. Sits around for an exceedingly long time until probably proton decay dissolves this brain sitting out in empty space or some low temperature de Sitter space. And eventually all those leptons and photons fly off and you've just got empty de Sitter space there. So how do I get it back? Well, I just go through, I wait for all those to assemble this desiccated brain that sits around for 10 to the 33 years or so. Eventually, strangely, all this water and all this glass kind of congeals on it, forms a jar, and eventually I get my brain. Now, there are some fun questions about the moment during which this brain becomes conscious that I don't want to go into, but maybe we could later. We had a long discussion about this and then finally decided that it was crazy to be talking about, but that makes a good fodder for this meeting. So my third example is stepping up in scale a little bit. How do we create a pocket universe? And so one way to think about this is that, so what I've drawn up on the top here is a sort of toy model inflationary potential. So the idea is that in that false vacuum up there on the left, it's high energy. That means low entropy when you're talking about a de Sitter space-like solution. So that's a high energy, low entropy inflation. There's a barrier that prevents the inflaton from getting over to this low energy, high entropy region. There are different ways you could get through that barrier. Quantum tunneling is one that I'll talk about in a minute. And another one is just because de Sitter space is thermal, the field can just fluctuate. And if you wait long enough, it will fluctuate over that barrier. And you can ask, what does that look like? So one thing you can do is imagine making a little blob, a kind of little stable blob of not quite the false vacuum. So it actually turns out to stretch. If you ask for a static blob, it turns out to stretch from the false vacuum over the hump a little bit into the true vacuum. And that blob, if you built it perfectly, would just sit there. It's just some field profile that will sit there for a long time. If it's a little bit unstable, it will then flop back into the false vacuum and kind of oscillate for a while and give off some waves of scalar radiation. But if it was perturbed just a little bit the other way, it could flop off the right-hand side down into the low energy, onto the low energy side, and that would then create some region of low energy inflation or non-inflation there. So that's a little pocket universe being created. Now you can ask, how did that get there? And the answer is simply like this. So if you ask, how did the failed baby universe get formed? It's the time reverse of how these modes kind of oscillate and drive the thing up into this configuration. If you ask, how did the successful bubble universe form? If you're starting out on the left-hand side, it would do the same thing. You'd have these oscillations that would lead you to the static configuration, which then by chance would kind of flop over into the other side. So rather than just having this vague picture of, well, it kind of fluctuates over, what's nice is that I think we now have an understanding of just what that looks like as it fluctuates over. You can also ask the other question, if I were in the low energy, high entropy inflation or non-inflation, how could I get back up there? And that again is just the time reverse, so it looks like this. This is a strange one where if this is our universe down here, you kind of have to replay the whole history of the universe. You have to, the galaxies have to unform, and the universe has to heat up, and the atoms have to get ionized and so on, and the perturbations have to go away, and you have to deflate, and then finally you can diffuse back over this thing at the very last minute. Now, it turns out this is usually not the most probable way to get over the hump. The most probable way is called coma and DeLucia tunneling, and for aficionados, there's the conformal diagram, and here's the conformal diagram for reverse coma and DeLucia tunneling. This has always been a really weird process to me because it takes this absolutely huge region of low energy de Sitter space and replaces it with a quite tiny one of high energy de Sitter space. That now makes sense because in fact what happens is you slowly shrink over, say, 15 billion years or 14 billion years or whatever, your universe down until it gets to the small size, and then it just quickly denucleates at the end. So what does this tell us about cosmology? Well, one thing is that when we're thinking about transitions between inflationary states, which you think a lot about in eternal inflation, we shouldn't really think of upward transitions where you go up in energy as sort of the same thing as downward transitions, but more unlikely. Instead, you really should think of them as time reversals that go where time reverses just for long enough to get us into this previous vacuum, which is previous and future, I get all confused now, but up to the higher vacuum. And now one thing I forgot to mention is that when we apply this to gravitating spaces, like this one, something I glossed over was this shading. So the shading here is indicating that we, consistent with the way Raphael would advocate, are really just thinking of the system as being the region within the so-called causal diamond of a particular observer. So this is the region that an observer at some place that follows a world line has access to, that can send signals to and receive signals from. So we're confining our attention to within that region. Now, something that's a little bit peculiar that eternal inflationists tend to do is to think of rewarding inflation for producing this huge volume out of a false vacuum. So the idea is, if you don't have inflation, but if you could just somehow get it, then it would create infinite volume for you. And so that makes lots of stuff that is post-inflationary, and so all the probabilities work out nicely. But what's unfair, I think, about that's suggested by this, not rigorously, but is suggested by this, is that it's a little unfair to give them that infinite reward, but not charge an infinite price, right, for creating that little bit of inflation, if it's really time symmetric like this. It's very clear within a single horizon that you have to do exactly that. You have to charge as much as you reward. If you go outside of that, which is the way people are thinking, it's unclear how exactly to think about it, but the flavor of it is a little bit cheating to me. Another question this leads to is, how did inflation start? So it could have just started, there might have been a singularity and we don't know, we can't say anything, et cetera. But suppose we don't say that. Suppose there was some previous higher entropy epoch, and we just want to make this lower entropy inflation region. So there are theorems in GR from Vachaspati and Trodden and Guth and Farhi that say this is very hard. You can't do it unless you have violations of the weak energy condition and so on. But it can happen. It can happen in two ways. One is by the baby universe mechanism, which I'm not going to talk about, where you create a baby universe totally out of causal contact from you. You can't access it or see anything about it. Or the mechanism that I was basically just talking about, where time reverses. You sit around long enough that you're in equilibrium, time reverses, and you create this inflating region. In this case, what we called the previous higher entropy epoch actually happens after inflation again. So wherever inflation is, it's to the past of where you are. So a sort of corollary is that if we just take some, sort of running the argument a little bit differently, if we take some time at which the universe is at what we call minimal entropy, and we say that there is equality of microstates within that macro state that we've specified, then I think it just is genuinely true in a very precise way that the arrow of time points away from that, this way and that way on the diagram. So this leads to pictures that are sort of like this, where we might say, I'm just going to specify the universe as like that, at some time, and then we can create, say, bubbles going that way, but bubbles would also go that way for just the same reason. And if we talk about a more complicated eternal inflationary space, where this is the sort of conformal diagram some of you have seen and will create horror in others of you, this is many bubbles bubbling off of some initial inflating space that I've just stuck here. As Sean has complained, most people just shade out the bottom and don't talk about it. But if you don't shade out the bottom, it looks like this. So if you've really specified that as just being in this false inflating vacuum there, this is the kind of picture you will see. You will also get bubbles pointed down the other way. And there are various versions of this that you can think about. The favorite version of mine, so you can take any space-like surface. The favorite version of mine that I worked out with Stephen Grattan is one where the boundary condition is actually a null surface, which has a lot of neat properties, but I won't go into those now. You can read the paper. So just to summarize, I think there are sort of two basic points. One is the precise statement that evolution from equilibrium to a chosen macro state A is the time reverse of the evolution from A's time reverse to equilibrium, with all of those provisos that you can read. Second, it is very hard to start inflation from non-inflation. This has been known for a long, long time. Other than the baby universes that you can't access, and I have various gripes with those, but that's a separate subject, you find that inflation comes first either way. You can't, if you try to create inflation, you find that inflation actually created you. But this may be a feature, actually, that allows pleasingly time-symmetric inflationary cosmologies, which people are starting to explore and I think are fun. Thanks.